So we'll just get started here in about another minute. There was a question in chat if there would be time to go over homework. We do have a lot of problems to get through, but I might try to keep a little bit of time right at the end if there are some homework problems that we can answer really quickly. And then there's a little bit of time before the next discussion. So we might be able to go a few minutes over for some homework problems. Awesome. So we'll go ahead and get started then. So for our first problem here, so we've got another problem with sequences. So we have this sequence defined both recursively by a sub k is equal to 2ak minus 1 minus 3. And then we have this initial condition such that a of 1 is equal to 4. And somebody has guessed that this is probably the closed formula, that a sub n is equal to 2n minus 1 plus 3. And so what we want to do here is we want to look, does this maybe seem right? And in a following problem, we'll actually prove that this is indeed the closed formula. So the first part, if you just want to take for parts A and B, just take a minute or two to write down what are the values for R1, R2, R3, and R4 using both the recursive formula and then as well the closed form formula. All right, so let's go ahead and start checking these. So first, in order to see if this recursive formula is true, we need to find out what are the values for A1, A2, A3, and A4. And these ones are going to be given by the recursive formula. So A1 we were given, that's equal to 4. A2 is 2 times the previous value, so 2a sub 1 minus 3. That's 5. And then a sub 3 is 2 times a sub 2 minus 3, which is 7. And then a sub 4 is 2 times a sub 3 minus 3, which is 11. Oh, that doesn't look very good. And that's just from the recursive formula. And then now we can check, do we get the same values if we used the closed form for each of the values? So for R1, for 8, we have that's equal to 2 to the 1 minus 1 plus 3. And that's equal to 4. 1 plus 3 is 4. R2 is 2 to the 2 minus 1 plus 3, which is 2 plus 3, which is 5. R3, 2 to the 3 minus 1 plus 3, which is 4 plus 3, which is 7. And R4 is 2 to the 4 minus 1 plus 3, which is 8 plus 3, which is 11. So yes, R1, R2, R3, R4, the values we obtained from the closed form formula, give the same values that we got from the recursive formula. So yes, this is true. Checking the first 4 numbers. Now, obviously, this would be a proof that this is indeed the closed form formula. But this shows us for the first 4 values that this is correct. So let's jump to the next part here, where we're asked to write down the values for R8 and R9. So for R8, since we have a closed form formula, then we just have that A8 is 2 to the 8 minus 1 plus 3. So 2 to the 7 plus 3, which is equal to 131. And for R9, we just plug into the closed form again. So we've got A9 is equal to 2 to the 9 minus 1 plus 3. So that's 2 to the 8 plus 3, which will give us 259. So here, just plugging into the closed form formula again, pretty straightforward. And then what we want to do is we're going to use these 2 values here that we've got for R8 and for R9 in order to see how we can verify whether or not R9 is correct. So here we suppose that we've already verified the value for R8. And then we want to see how could we verify that R9 is the correct value without starting all the way from a sub 1, a sub 2, a sub 3, et cetera, et cetera. So anybody have any ideas for this one, either in chat or just by raising your hand? So here we're assuming we already know the value. We already know that R8 gives the correct closed form value.
Can you just use recursive form?
Yeah, exactly. So to verify R9, let's just use the recursive formula. So a sub 9 is equal to 2a8 minus 3. We know a8 is the correct value, so we can go ahead and plug that in. So that'd be 2 times whatever R8 gives, minus 3. We solved this on the previous page when we found what R8 was. And for R8, we can go ahead, we can use the closed form formula just so you can really see it here. So we use the closed form formula for R8. So we have 2 to the 8 minus 1 plus 3 minus 3. And this will be 2 to the 8th plus 6 minus 3, which is 2 to the 8 plus 3. And that would be 259. And this looks correct. This is exactly what the closed form formula would have given right here. So we started with the recursive formula. And we ended up here, if you look at this formula right here, this is exactly what the closed form formula would have given for R9. So we can verify that R9 is correct. So the closed form formula works for R9. So are there any questions with this first problem, any parts A, B, and C for this one? Awesome. Pretty straightforward problem, but now we're going to look at actually proving that this is indeed the closed formula, right? So we have the same sequence again, given right here. And what we want to do is we want to prove that this closed formula is correct. And so we're asked here to do a formal proof of this, and the hint is that we want to use induction in order to do this proof. So whenever we have induction, right, there's kind of those 4 steps that we always want to go through for any induction problem. So the first one, we're going to have the problem statement. So we want to introduce P of n. So someone want to explain what could we have for the problem statement? Or what's our problem statement for this problem? Yeah, we do want something. Yeah, so we've got in chat that a sub n is equal to a sub n. That's close, except that's kind of, you have the right idea, but that's kind of just saying that the closed formula is equal to the closed formula. And so what we want to do, and Jacob's got another idea, so a sub n is equal to a sub k. And that is nearly right. But there's just one extra piece that we need there. Because we need to remember that we include the base case as well. So we don't just want a sub k to equal a sub n, but we also want a sub 1 to be equal to whatever a sub 1 is given by the closed form formula. So one way we could say that a sub k is equal to 2 ak minus 1 minus 3, and a sub 1 equal to 4 is equivalent to a sub n is equal to 2 to the n minus 1 plus 3. Yeah, so somebody else in chat, yeah, pretty much the same. Similar idea, yeah. Except we just also want to make sure that we specify that we also want the base case to be correct. Awesome. So then we've got the problem statement. So next part of induction is the base case. And yeah, we've got a question on the base case. So someone is asking, wouldn't the base case be a sub 1 is equal to a sub 1? Not exactly. We are going to look at a sub 1 for the base case, but that's kind of what I was explaining before, is this a sub 1 equals to 4 is only given in the recursive formula. But it says nothing in the closed formula about the value of a sub 1. So you want to plug in the value of when n is equal to 1 for this closed form expression here to verify that that is indeed 4. So you have to prove that p of 1 is correct. And so we have that a sub n is equal to, if we plug in n is equal to 1, that a sub 1. Another question in chat, yeah, but if both are a's, wouldn't it be confusing? It is a little bit confusing, I will give you that. The reason being that both of these are, yeah, that we have a sub k, a sub 1, and then this a sub n that we want to be the same. Which is why we have to be a little bit careful in how we specify the problem statement and needing to describe them as equivalent. But we just want to verify that the closed form gives the same thing that the recursive form does. Oh, yes, that's a great, yes, great point from Mohammed. So I thought in the problem statement, n would be the only variable since we have p sub n, where n is the independent variable. Yes. Yes, you are correct. That is a very good observation. So what was pointed out is that we actually didn't specify what the value of k was when we introduced the recursive formula, and because the problem statement p sub n only knows what the value of n is, we needed to change that. So yeah, that was a really good catch. Yeah. So now we can go back. So with proving p sub 1, so we've got a sub 1, just verifying that the closed formula, what the closed formula gives, a sub 1 is 2 to the 1 minus 1 plus 3. 1 plus 3 is equal to 4. And a sub 1 equals 4 from the recursive formula. So our base case has been shown. We looked at what the closed form gave. said, hey, that's exactly what the recursive formula gave to us. So our base case is true. Then the next part of an induction problem, we always have the induction hypothesis. So what would our induction hypothesis be for this problem? Does someone want to raise their hand or type in chat? Yeah, basically, yeah. So somebody's put in chat, the induction hypothesis is, yeah, that P sub n is true. Yeah, so P sub n is true. Or in other words, if we just expanded that, we assume that basically A sub n equal to 2a n minus 1 minus 3, a1 equal to 4 is equivalent to the closed form. And then with this assumption, if we're assuming P sub n is true, then in the inductive step, we're going to need to prove that P of n plus 1 is true. We could have also, in the induction hypothesis, we could have assumed that P of n minus 1 is true. And then in the inductive step, we could have shown that n was true. But yeah, this will work perfectly. So before we start the inductive step, did anybody have any more questions on either the problem statement, base case, or the induction hypothesis for this problem? Awesome. Or, okay, we do have a question. So I know we use the induction hypothesis for substitution. Yes. So in the inductive step, we're going to have some part where we're starting with the recursive formula because we know the recursive formula is true, and we want to end up proving that the closed form is true. So there's going to be some point in the recursive formula where we're going to be able to substitute in, where we're going to be given this, and then we can substitute in for the value of our closed formula. And we'll take a look at where that happens in the inductive step. So here we want to show that P of n implies that P of n plus 1 is true. So for this problem, because we're given the recursive formula, and then we want to prove the closed formula is equivalent, we need to start out with the recursive formula. So we have that a sub n plus 1 is equal to 2 times a sub n minus 3. And this is just exactly what the recursive formula gives. And so that's where we have to start. But something that we know from our induction hypothesis is that we know the closed formula for a sub n is correct. Right? We assume that the recursive formula works for a sub n. So what we can actually do in this next step is we can do that substitution that Lance was talking about in the comments for our induction hypothesis. So the closed formula for a sub n that we assume to be true is that a sub n is equal to 2 to the n minus 1 plus 3, minus 3. And then this is by the induction hypothesis. And that's how we can get to this next line, because we assume the formula is true for a sub n, so we can just do immediate substitution. There's a question in chat: when do you use P of n plus 1 versus P of n minus 1? You can really use either. So there's kind of the two most basic things you can do is you can either assume P of n is true in your induction hypothesis, and then you show that P of n plus 1 is true. Or you could assume P of n minus 1 is true, and then show P of n. Either works out, either is perfectly correct, and it'll sometimes just depend on algebra, which one of these two will work better. But you can pick whichever one you like to use more. They both work. So yeah, so we did the substitution by the induction hypothesis here. And then we basically just need to simplify the expression. So multiply 2 through, so we get 2 to the n, plus 2 times 3 is 6, minus 3, which is equal to 2 to the n plus 3. And that's exactly what we wanted to prove. We wanted to show, right, that a sub n is equal to 2 to the n minus 1 plus 3 is the correct closed formula. So when we add a sub n plus 1, that should be equal to 2 to the n plus 3, as shown there. And that's exactly what we have here. So thus, the formula holds for all n greater than or equal to 1. So any questions on this problem with induction? No? Awesome. So now we can get started into kind of what was covered this week with a problem on the pigeonhole principle. So with this problem, we're given 5 integers. Could be any integers, positive, negative, doesn't matter. So we have any 5 integers, and then we want to show that 2 of them will have either a sum or a difference that is divisible by 7. So whenever we have a pigeonhole problem, what we always want to go back to is that pigeonhole theorem that we have that introduces the variables that you may remember, m and n, to count the number of boxes and the number of items that we're putting in our pigeonhole. So what we want to notice here is that we have 5 items, right, total. And then we know that there's going to be at least 2 values that have a sum or difference divisible by 7. So can anybody tell me either in the chat or just by raising your hand, what are the formulas that we're going to have for this problem with our m and n? Yeah, so someone said in chat, because we know we have 5 total items given by we're given any 5 integers, that then we let m times m plus 1 is equal to 5, where this is the total number of items. They'll always be the case in any pigeonhole problem. And then what we also have is that there's 2 that have a sum or difference divisible by 7. So this is what the number of items we're going to be guaranteed to have in one box by the pigeonhole principle. And as somebody said in chat, the formula for that is that m plus 1 is equal to 2. And this is the number that we have at least this many items in a box. So these are the 2 formulas given by the pigeonhole principle for this problem. And then we've got 2 formulas, 2 equations, 2 unknowns. We can solve for them, right? So by solving, for m and n, we have first, so m plus 1 is equal to 2, so m is equal to 1. And then if we plug m equals 1 into the first formula, we'll have n plus 1 is equal to 5, or that n is equal to 4. And can anybody tell me what's so important about what the value n is? What does the value n represent for us in a problem on the pigeonhole principle? Yeah, so we've got some answers in the chat. Yeah, the number of containers. So n equals 4, and this is the number of containers, or the number of boxes. And so now we've kind of solved for all the information that theorem on the pigeonhole principle gives us. So what we can say is that since n is equal to 4, we want to have 4 boxes. And then we want to kind of start thinking about, so we know we have 4 boxes just by solving these equations. But we want to think about what can we put into the boxes. We're going to be putting integers, but we want to have some special way to place integers in this box. So go ahead and take about a minute or two and kind of think about what items could we put in these boxes to make this problem work, so we can show that the sum or any difference of 2 items in a box is divisible by 7. Let's go ahead and think about that for a little bit. Awesome. So we've got some really good answers coming into chat, and they all pretty much deal with the same thing. So we're going to be looking at the remainder of a given integer when we divide it by 7. And so some of the ideas that we had as well, let's put all the items that have remainder 0 into one of the boxes, that have remainder 1 and remainder 6 into a box, that have remainder 2, remainder 5 into a box, and remainder 3 and remainder 4 into a box. So why do we pick these? Why do we pick these values? The reason why is because we wanted to place integers in a box where the sum of the two integers would be divisible by 7. So right, if you took anything remainder that when you divide, you had remainder 0 and you added them together, you'll get something divisible by 7. Something with remainder 1 and remainder 6 would be divisible by 7, 2 and 5, and 3 and 4, because all those add up to 7. So that's kind of the idea that we want to use for this problem. And this is really kind of the hardest part about any pigeonhole principle problem, is you have to kind of figure out what items are you going to put in boxes that's going to make the problem easier to solve. So it can be a little bit tricky. So don't feel too bad if you didn't immediately see this. It takes a lot of practice to be able to kind of see some of these tricks for these problems. But yeah, this will work for us. So we're going to have, basically, I'll just write this a little bit more formally. So we're going to create 4 boxes. And then we're going to take, I guess I'll explain it this way, and we're going to take the remainder. So we're going to take a number and divide by 7. We're going to place it into the corresponding box as described above. So we can write out a little bit more formally, but we're running out of space. But the idea being, just take whatever remainder, and then if it's 0, you place it in this box. If it's 1 or 6, you place it in this box, etc. This box or this box. So now we've kind of created the boxes. We know what the numbers are. Now we've got to prove that this works. So we've got to prove that we're guaranteed that at least two numbers will have a sum or difference divisible by 7. So the first thing that we need to point out is we need to be guaranteed, first of all, before we can even start talking about whether or not two of these integers have a sum or difference divisible by 7, we got to prove that there's actually going to be two integers in a box, in one of these boxes, before we can even start talking about whether or not there's a sum or difference. So can anybody tell me, why are we guaranteed that one of these boxes is going to have at least two integers? Yeah, somebody said, yeah, there's 5 integers, 4 boxes. Pigeonhole principle, we know one of them's going to have 2. So that's the first thing we need. So by pigeonhole principle, one of the boxes will contain at least 2 numbers. So now we've got to go through all the cases to show what if box 1 had 2 integers, what if box 2 had 2 integers, and 3 and 4. So we have 4 cases. And what I'm going to try to do is hopefully to be able to describe, because it's like a little bit of time to write out, hopefully we can describe all of these cases kind of together. So first, let's take a look at what happens with box 1. So everything has remainder equal to 0. So how in the first box, it should be too bad to see why we're guaranteed that either the sum or difference of any two values will give a remainder 0 when divided by 7. Right. So I guess what we could do, let's make this just a little bit formal for this example. So we could do something like let K1, K2 be elements of box 1. So we got 2 numbers, K1, K2 in the box. Then K1 is equal to 7 times, let's say some constant C1. And K2 is equal to 7C2. And why do we know this? Well, we know this by the division theorem. And then we just have to either show that the sum or difference of any two is divisible by 7. So here we could show this is true for the sum. So then K1 plus K2 is equal to 7C1 plus 7C2, which is 7 times C1 plus C2. Thus K1 plus K2 is divisible by 7. And that would be enough to show us for box 1. We don't actually have to show the difference. And the reason why is just because we had to show that one of these two cases happened. Either there's 2 that had to have a sum or 2 that had to have a difference. And it turns out in box 1 that both of those happen regardless. Any 2 number integers you pick in here will have a sum and a difference divisible by 7. So we can just show the sum and make it a bit easier. So there was a good question in chat. How do we remember all the theorems? So I was bringing up the pigeonhole theorem, the division theorem. The trick, you just kind of have to spend some time memorizing some of those theorems. You only need to memorize the big theorems that we talk about. So like the division theorem is a big one. The pigeonhole principle, that's another one. Is there a single PowerPoint with all these theorems? I don't believe that there's a single one with all of those, but it's really the big ones that we spend a lot of time talking about. So for example, like theorem 2 in the text, you don't need to memorize that. That was how we dealt with equivalences between statements. You don't need to memorize that one. Division theorem and pigeonhole are the ones I can think of off the top of my head that are the really big theorems that we need to know. And yeah, I don't know if there is a cheat sheet made, but you can definitely make kind of like your own study sheet and write down all the big theorems that we talk about would be helpful. And then there was another question in the homework problem. We have a lot more boxes. So how are we supposed to prove them all? Yeah. So yeah. For one of the problems. So what you can do is you can talk about any. So let's actually try to do that for this problem, because what you do like in the homework is you basically talk about some box in very abstract terms. So you say, let's pick some box out of the set of boxes, and you really generalize the theorem that you're using conventional principle for. So that way you don't have to do like, I don't know, if you had like 100 boxes, you don't have to do 100 cases because it'll be a really long proof. So we can talk about a box in general. So let's try to do that for this problem. I think that would be really good practice. So we're going to try to prove all the cases for box 2, 3, and 4 together in just one statement. So this will be the proof for box 2, box 3, and box 4. So somebody said in chat, you can make a note on Piazza for people to draw proof techniques. Yeah, that'd be a good idea. And then somebody could even start a chat if you want to, like, you can start a discussion thread on Piazza if you want to have like, if you want to work to compile a list of all the important theorems. Yeah, that'd be a great one. So we got boxes 2, 3, and 4. And so remember, box 2 contained the remainders 1 and 6, 3 contained the remainders 2 and 5, and 4 contained the remainders 3 and 4. But what each of these had was that in each box, let R1, we're going to let R2 be the two remainders. For each box. So in each one of box 2, 3, and 4, they each had two remainders. No matter what box we pick, we have R1 plus R2 is equal to 7. No matter which of these boxes we pick, box 2, box 3, or box 4, the sum of the remainders in the box is going to be 7. Then we have two additional cases. So let's imagine, so we've got this box and there's two types of items in the box. We've got either a remainder R1 or a remainder R2. And I want to pick two integers out of that box. Well, there's two cases. Either both of them have the same remainder. So I happen to pick two integers with remainder R1, or I pick two integers with remainder R2. That's the first case. And then the second case is I pick two integers that have different remainders. So one of them has remainder R1, and the other one has remainder R2. And those are the cases that we're going to cover here. So for case 1, we have that integer, let's say that K1 is equal to 7C1 plus R1, and K2 is equal to 7C2 plus R1. So somebody said, could we also equivalently have explained the R1 plus R2 equal to 7 as R1 minus R2 is equal to 0? Not quite. We're not guaranteed that because, for example, box 2 remainder has 1 and 6. 6 minus 1 is -5, and that's not equal to 0. Oh yeah, for one of the cases. Yeah, so we could say that the difference of the remainders is 0 for this first case. Yeah. Oh, yeah, when I was talking about remainders, we're talking about divisibility of integers divisible by 7. So I'm talking about the remainder when we divide this integer by 7, just because that's what the problem is talking about. So for the case, we have that R1 is equal to R1. And then K1 plus K2 is equal to 7 C1 plus C2 plus, whoops, that won't work for sum. So this is where we're going to use difference for this case here. We can either show that the sum or difference of any two integers is divisible by 7. And it turns out it works really well if we do the difference for this case. So 7C1 plus R minus 7C2 plus R. And then we'll end up with 7C1 minus 7C2, which is 7 times C1 minus C2. And that's divisible by 7. Because that's remainder equal to 0 by the division theorem. It's divisible by 7. And then running out of space here, but then for the final case, case 2, we'd have that the remainders are not equal. So 7 equals 7C1 plus R1. And K2 is equal to 7C2 plus R2. So here, then we're going to look at the sum. So K1 plus K2 is equal to 7C1 plus R1 plus 7C2 plus R2. And this, remember, we said that R1 plus R2 is equal to 7 for every box. So this is just going to be equal to 7C1 plus C2 plus 1. And this is divisible by 7 by the division theorem because this has remainder 0. And so this would have covered all the cases because if we were in box 1, we proved that there were two integers that has sum. And then if we were in box 2, 3, or 4, we proved that either, hey, these two numbers have the same remainder, in which case the difference is divisible by 7, or they have different remainders, in which case the sum. So the theorem is true. So anybody have any questions on this?
Wait, how did you do the case 2? Could you just go over that one more time? Sorry.
Oh, sure. Yeah. So for the case 2, for this one, we're assuming that the two integers we picked have different remainders. So we're assuming that one of them, K1, has a remainder R1, and then K2 has a remainder R2. And remember that for each of the boxes 2, 3, and 4, the sum of the remainders was equal to 7. Box 2 had remainders 1 and 6.
Okay,
Box 3
got you now.
had remainders 2 and 5, and then 3 and 4. And so that's how we were able to say, hey, when we add these two numbers, R1 plus R2 is equal to 7. Yeah, great question. Oh, and we got a question in chat. So what if both integers make a number smaller than 7? Yeah, so that was answered. Yeah, perfect. That would still have remainders between 0 and 6. Division theorem holds for any integers. And then there was another question in chat. So we have to assume that all R1 and R2 were put into a box in a way the remainder plus the other is 7. Yeah. And the reason we know that is because that's how we defined the boxes. We created these really nice boxes such that had that property that made the proof work. So yeah, and that's what I was kind of explaining earlier. This is really the most important part of a pigeonhole problem, is you have to figure out how to construct these boxes so that the problem works out. So they have properties that you want to be able to utilize later. So any other questions on this problem with pigeonhole principle? Yeah, pigeonhole principle problems, they do take a while. I would just recommend doing a lot of example problems. Just because once you start to do a lot of these problems, you'll start to figure out some of the patterns that they have. So someone had a question. So does pigeonhole principle technically not work for all integers? It's not just about like all integers. It's it's really about containers and being guaranteed that you have at least some number of objects divided by containers. And it turns out it's really useful in a lot of applications to be able to describe that. And then, yeah, so I'm seeing a lot of other questions a little bit off topic with CS3500. So if you could just talk about that maybe after the discussion is done, you could reach out to people in the class later. That'd be great. So let's go ahead with whenever we're done with this. So somebody else had a question. So you set the constraints for the proof. Yes, you have to set these constraints. So that's why with the pigeon problem, we have to do all this solving here to figure out what number of containers we need, the total number of items, and then we need to put some constraints on each of these boxes for it to work. Yes, and then we'd prove that it works under these set of constraints that we have for the boxes. And yes, like Brendan was saying, we could have had two numbers that were identical, and we covered that in case one, where they were two numbers that had the same remainder in both boxes. Yeah, really great questions there. So let's go to this next problem. So we've got this contrapositive proof. So we want to prove the following by contrapositive. For all real numbers x and y, if x squared plus y squared is not equal to 0, then either x is not equal to 0 or y is not equal to 0. So does somebody want to give me what's the contrapositive of this statement? Yes. So we remember for contrapositives, if we have P implies Q, the contrapositive is not Q implies not P. So the contrapositive here is, like there were a bunch of answers in chat, if x equals 0 and y equals 0, then x squared plus y squared equals 0. So let's try it. So let x equal 0, y equals 0, then x squared plus y squared is 0 squared plus 0 squared, which is 0. Thus, the statement is true. If the contrapositive is true, then the original statement is true. So this problem is not too bad. But what I want you to notice here is how much easier the problem becomes if we look at the contrapositive versus a direct proof. So directly proving this statement would have been a little bit trickier because we've had to know that hey, x squared plus y squared is not equal to 0, and then we need to do a little bit of work in order to show that either one of these two cases happens. X is not equal to 0, y is not equal to 0. But when we come to hard problems, oftentimes looking at the contrapositives of the statement can make it really easy to solve. So like in this case, this is nearly trivial to solve with the contrapositive. If x and y are 0, then yeah, the squares are going to be 0. So that's just something to remember when doing proofs. We'll often tell you if you need to use the contrapositive, but just thinking about it in later classes and down the road when you're looking at proofs, oftentimes the contrapositive can really simplify a proof. Not always, but sometimes it definitely can. So any questions on this one? Awesome. So let's go ahead. This is probably the last one. Actually, somebody did ask about if we could leave a little bit of time because somebody had some questions on some of the homework. So we can go ahead and, since we've got about 2 minutes left, if you have questions on the homework or whoever that was, if you just want to kind of go ahead and ask what your question was. No questions on the homework then? Oh, there we go. Okay. So they had a question on, so let me actually see if I can, so we can all be looking at the same problem. So let me stop this screen share and so hopefully everybody can see the screen here. So there was a question on part 11. So on the induction, you report where it's time to substitute, but there's no clear substitution. Yeah, so for this one, you're going to need to work just a little bit to kind of think about. You're going to need to do just a slight clever factoring of 2 to the 3n. So just remember some of your power rules. And you should be able to see a time when you can substitute in for a known value. Also, what I would recommend for this problem is try it for n equals 1, we start at 2. So n equals 2, n equals 3, n equals 4. And you should be able to see a pattern in what 2 to the 3n minus 1 gives. And that's where you're going to need to use that substitution. And then there was another question. So question 13, multiple cases are good to show that if we subtract 2 integers and then it's divisible by 100, is divisible by 100. Is that good? No, you're going to need to do a little bit more work than that because you need to show that just amongst the set of 52 integers, that there's going to be 2 of them that have that difference. And so what you're going to want to do is, like we did earlier today, solve for the total number of boxes that you need in this problem. And then it should just be an application of the pigeonhole principle to show you if you have 52 objects going in this box, you're guaranteed, if you set up your boxes correctly, that in one of those cases, the difference between the integers is going to be divisible by 100. So you're just going to need to set up your boxes in a special way. So yeah, what I mean there is that you just need to show that based on how you set up your boxes, at least 2 objects have to fall into that box. And if 2 objects fall into that box, then they must be divisible by 100. So I don't think for this problem you actually need multiple cases if you set up the boxes in a correct way and you kind of do what we did for this last pigeonhole problem, where you talk about boxes in general. That'll really help. So awesome. So we're about out of time then. If you have more questions, what I recommend first is that you go through the other 2 examples. From these slides, there's a great little problem on a basic induction proof. That'd be good to just kind of refresh yourself on, especially before we get to the quiz on proofs. And then if you have any questions, please stop by help hours or office hours, or post more of your homework questions on Piazza, and we can definitely help you that way. It's awesome. We'll go ahead and end it there. Hope you all have a good rest of your day.